Hi, I'm Emily Blem, and in this video I will provide a summary of our work, Power Challenges May End the Multicore Era, which appears in the February 2013 edition of the Communications of the ACM. This paper is based on our ISCA 2011 publication, Dark Silicon and the End of Multicore Scaling. For this video, I'm going to start by talking about the history of microprocessor trends, specifically the transition from early cores to today's multi-core chips. I will then briefly discuss how we use models to anticipate future trends, our findings, and the implications of these. Let me first give some historical background on the drivers of microprocessor performance, Moore's law and Dennard scaling. In 1965, Gordon Moore proposed a result which became known as Moore's law. He observed that the number of transistors per chip had doubled during every technology generation up to that point, and suggested that he saw no reason why the trend could not continue for the next 10 years. This figure from Moore's original paper shows the observed and projected growth in the number of transistors per chip per year. The trend has continued well past those 10 years, in fact it's now been close to 50 years, and with it, consumers have come to expect an increase in performance every generation. A physical driver for Moore's law was published by Robert Dennard et al. In 1974. They made the observation that as MOSFET area is scaled, capacitance, voltage, current, and delay can all be scaled at similar rates. As a result, as transistor area scales, power remains constant. This table from the original paper shows the scaling factors and equations used to find the factors for current and voltage. This implies that each technology generation, transistor speed and density can increase while power remains constant, allowing Moore's law to continue. Until 2004, Moore's law combined with Dennard scaling allowed chip manufacturers to increase frequency by 40% each technology generation, while voltage and capacitance were each scaled by 0.7x. Combined with increasing chip sizes, performance increased while power remained approximately fixed. In 2004, leakage issues due to the increasingly tiny transistor sizes meant that voltage could no longer be scaled. Without voltage scaling, manufacturers could no longer increase frequency without significantly impacting the power budget. Dennard scaling no longer held. Instead, chip manufacturers turned to multi-core chips, placing multiple cores on a single chip to achieve performance improvements through parallelism. In this work, we look to the future and ask, is multi-core a long-term solution from this point on, or was it a decade-long stopgap measure? In our work, we answer the previous question using models of device properties, the trade-offs between core performance, area, and power, and the interactions at the chip level of real applications, the multi-core topology, and chip characteristics. At the device level, we use technology projections to predict area, power, and frequency trends at future technology generations. At the core level, we use real core performance, area, and power data to find corresponding trade-offs for a wide range of state-of-the-art processors. Finally, at the multi-core level, we use analytic models to find the overall chip performance considering a full range of important characteristics, including chip topology, CPU and GPU-like cores, constraints including chip bandwidth and cache sizes, and real application characteristics. The paper has a detailed technical description of all of our models. By combining the three models, we are able to project performance across a wide range of cores, topologies, and applications at future technology generations. In the next slide, I will describe the key findings we obtained using these models. Using our model to perform a state space search at each technology generation, we project performance across a well-known parallel benchmark suite called Parsec. We set as an aspirational target performance improvements similar to single-core improvements prior to 2004, resulting in a targeted 18x speedup over 5 technology generations. Using our optimistic modeling approach, we find that projected speedups are only between 7.9x and 3.7x, depending on the device model used. Moreover, we use our models to find the amount of the chip that cannot be used due to power limitations, also known as the amount of dark silicon. Here, we graphically depict the amount of dark silicon each technology generation by shading the unused portions of the core. We find that by the time we get to 8 nanometer transistors, over half of the chip is unused due to power limitations. Additional findings are in the paper, and interested viewers are invited to explore the results further using our web model at the URL on this slide. I will conclude this video by briefly talking about the implications of our findings, which we develop in more detail in the paper. A pessimistic interpretation of this study is that the performance improvements to which we have grown accustomed over the past 40 years are unlikely to continue with multi-core scaling as the primary driver. However, we believe that the key opportunities are to look beyond multi-core to new approaches. These approaches beyond multi-core are wide-ranging and include microarchitectural improvements, increased efficiency through architectural specialization, new device abstractions beyond digital logic, unconventional processing paradigms, and program semantic abstractions that allow for probabilistic and approximate computation. Our results show that such radical departures are needed, and the model provides quantitative measures to examine the impact of such techniques. Researchers are already beginning to look in these directions. The next 10 years in both computer architecture research and in the field will certainly not be dull.